All right, good morning, everybody. Welcome to the fourth session and the second session on machine learning and artificial intelligence. In this session, we are going to have three speakers. And the first one is going to be Tamit from Emad, from the University College of Dublin. And he's again going to talk about physics-informed machine learning. I will start the screen sharing now, and it would be nice if the online attendees could just give me a quick feedback as soon as possible that the slides are actually working.
Hi, everyone. As you can see, the title of this presentation is Machine Learning Enhanced Solution of Problems in Linear Elasticity. My name is Emad Tandis. I'm a postdoc researcher at University College Dublin. And I'm working on a project called SmartSim. This project aims to improve the accuracy and solution speed of problems in linear elasticity. And actually, my role is to improve the solution speed. So we know that iterative solvers are at core of many simulations in computational mechanics, and mostly because the problems in this field are nonlinear. So we have no choice but using, mostly this solver. The convergence history of this solver more or less are something like right-hand side figure. And as you can see, the residual, it requires some iteration in order to converge to desired level. So if we can reduce the number of iterations, it means that we can decrease the solution time. There are two ways or some other ways, but one way is actually using a better algorithm. For example, the blue line shows a better algorithm for the solution procedure that we have to implement a new algorithm, or alternatively, we can use good initial data, which are close to final solution. In that way, we can also accelerate the solver. You can see that in green line. So initial solution can be generated by a solution of low fidelity models, for example, solution on a coarse mesh, and then interpolate the solution for fine mesh. Alternatively, we are using here machine learning as initializer for the iterative solver. So what does ML initializer look like? We have problem configuration, and then we give it to iterative solver, and it gives us the solution field. So problem configuration means mesh, boundary condition, material properties, and also initial field. Iterative solvers means that we have implemented equation, discretization procedure, and solution algorithm, and at the end we have solution field. So for machine learning, we want to have a black box which receive the configuration, or at least part of the configuration that we care about, and receive the solution field. And since we cannot really rely on the solution field given by machine learning models till now, we use it as initial field for the iterative solver. So we can accelerate the solver at least in that. So what is machine learning model? This is a black box. It receives input and it gives us the output. We can train it for every input and output which are related to each other. But it also comes at some expense. We need to put time for that. But what is this neural network? The neural network is actually a mathematical function, which is a symbolic function between input and output. So we have U as the output here, and input is defined there. So in order to train a model, actually we need to find W. W are weights of the network, which is related to complexity of the network and architecture of the network and the way that we want to apply that. So in order to train such a model, we need to define a quantity named loss. Loss in the classical supervised is difference between the true data and prediction. We want this difference comes to zero. So when we want to train a model, actually we want to minimize loss with respect to weight of the network. In that way, we find the weight of the network that the prediction get close as much as possible to the true data. But this approach requires true data. For our case, it requires prior solution. So we need to solution many problems before starting the training process, and that requires time. Another approach is physics-informed. For physics-informed, we define loss as the residual of the governing equation. In that way, we avoid using true data, but it also requires evaluate gradient and divergence operators, which requires some tricks. There is a method called PIN, which uses automatic differentiation in order to evaluate this gradient and divergence. Alternatively, we have used finite volume method because we wanted to use the results be consistent with the finite volume procedure in order to be used for OpenFOAM. So we have used both of the approach in this study and compared them together. As I said, the first approach is normal approach, classical approach, and requires true data, but the second approach is more complex for implementation and does not require any ground truth data. So the application of ML initializer that we want to check here is to solve a problem, a base problem with many configurations. And here we focus on different geometries of the same problem. Imagine that we have a problem with different geometries and we want to see what is the effect of geometry on the solution field. One way is to use regular CFD or regular OpenFOAM solver to solve one by one without taking advantage of the prior solution. Another way we have followed here is to use solution of n of this configuration as the data set, and actually train a machine learning model in order to be used as initializer for the other m configurations. So, and if you want to compare it with the regular solution without ML initializer, is if there is really benefit in that. For assessment criteria, we have used 3 parameters here. One is error, which is the prediction is actually here prediction is compared with the solution given by OpenFOAM solver. And we have kind of prediction accuracy here. A speed up is a kind of measurement, the how ML initializer decrease the number of required iterations for the solution procedure. And the last and most important parameter here is effectiveness. Effectiveness actually shows the computational time with and without ML initializer. So it accounts for overhead computational time for training, data generation, and so on. So if this is more than 100, it means that there is a benefit in applying machine learning initializer. So we have actually we have developed a piece of code that allows us to embed a pre-trained model within the OpenFOAM solver. It can be used for other problems, not ML initializer. So it's kind of a general library, and it's not public yet. We will make it public. So we can use it to use a ML initializer to generate initial data for the solution field. One case, actually we have studied 3 cases. One case is very similar to classical plate in a hole in a plate actually. And this is classical problem in Statistical-FOAM and OpenFOAM. And the parameter we have changed here is radius of the hole. So we have these geometries as the training data set, and the input is actually cell coordinates of this mesh for the network. So here we can see the convergence of the training process. In training process of the neural network, we have loss versus epochs. Epochs is kind of iteration in numerical methods. And we have also parameters called beta. This is fixed. People usually don't manipulate that. But here we have shown that this beta is kind of relaxation factor, can affect the solution procedure and the convergence speed. And the prediction here in qualitative way are compared with the reference data in the middle, which is generated by OpenFOAM. And as you can see, supervised and physics-informed relatively, give the same contours. And for the second case, these are unseen cases, which means that they have not been in the training process. So in quantitative way, here we have compared them together. As you can see in the 4th column, the training process for classical supervised requires much less time compared to physics-informed approach. So that means physics-informed approach is not really beneficial in terms of computational time. And last columns shows the two last columns shows the accuracy of both of the model compared to the OpenFOAM results. And as we can see, both of the model more or less, I mean, give the 5% accuracy. It depends on the training time you want to put. And when we use them as initializer for the iterative solver, we can see such behavior. The red line is the convergence given by ML initializer, and the black line is without ML initializer. The second test case is a circular plate, and this plate is constructed by 2 arcs. Each arc is constructed by 3 points. These points are randomly generated. So we have geometries such as this for the training data set. Again, we have compared the convergence in the training process. We have compared the results with the OpenFOAM for physics-informed and supervised model, and for the second case as well. And in quantitative way, we have also compared them together. And as we can see here, physics-informed is not really beneficial in terms of computational time. However, it can give good accuracy compared to classical approach. Again, we have embedded them in the solvers, and we have used them for acceleration of unseen cases. The same behavior have been observed. The third test case, which is more challenging case for iterative solver, especially in OpenFOAM, which are segregated. So this cantilever beam, when the length of the beam increases, actually the solution speed requires much more iterations, and it is because of a strong coupling between components of the momentum equations. So if we use ML initializer, we show that the benefits for such a problem actually can be much more. Again, we refer to the scenario that we had. We have K configuration from the same problem. N of them would be used for a training data set, and M are being actually accelerated by the ML initializer. The number of cases for M are 500, and N varies between 10 to 600. And here this table shows the effect of that. So when we use just 10 samples, the effectiveness, the far right column, is 181%, which shows that if we train a machine learning model with 10 samples, 10 prior solution, we can accelerate the other M100 samples. And if we increase the number of samples in the data set, which means increasing N to 80, we can see it accelerated more. And after that, it started to have bad convergence. So in a diagram, we can see something like this for effectiveness. So for 80 samples, as I said, and as it's shown in table, we have better effectiveness, the best effectiveness. So this is the optimum point. Also, we have used such a model for different size of mesh to make sure that it works with different size of mesh, not for coarse mesh. And we have seen the same behavior, sometimes better, sometimes worse, but more or less about 250% effectiveness. And also we have increased the length of the beam. And we wanted to see that because, as I said, when we increase the length of beam, the iterative solver, are not that effective. And you can see for length between half and 1, we have had 250% effectiveness. For length between 2 and 4, we have 461%. So I have concluded that for nonlinear problems, which require much more iteration, more than maybe, because these are the number of iterations here are about 5,000. So I would say, for example, if the solution process requires 10,000 iterations, that would be much more effective. So in conclusion, we have said that if we want to solve a number of simulations from the same problem, for example, for problem like optimization, for parameter analysis, sensitivity analysis, such algorithm can be beneficial in terms of computational time. And also we guess that this approach can be also beneficial for other problems that have these conditions. And physics-informed approach was not really beneficial here because it required much more time. We thought that because we don't need prior solutions, so it would be faster, but actually the overhead time is much more, and we cannot justify it till now. And at the end, we have built a workflow for applying machine learning model within OpenFOAM, and it can be used for other purposes. So I'm grateful for the funding by IRC and Baycart. Thank you for your attention.
Thanks a lot, Emad, for this really clear presentation. I will take the liberty and ask the first question. So the first thing that came to my mind seeing these numbers is that, have you tried to implement this in an online fashion? So let's say you run a couple of simulations, or you run one simulation, you train your model, and you already use it to accelerate the training or the next solution, right?
Yeah.
And then you update your model, you create a couple of more simulations, you update your model, right? And I think this could, again, accelerate the entire process because you would start training on fewer data. So before I finish, please, can you just repeat the question in a short manner for the online attendees? So the question would be, have you tried to train, to implement this workflow in an online fashion?
In what? Sorry.
In online fashion, like incrementally, creating data, updating the model, creating data, updating the model.
You mean further training after it is trained?
Yes, yes.
Oh, okay. I have
trained with very little data, and then training the model, right? And then using the model already to accelerate the generation of the next data sets.
Yep. That's a good idea. I mean, I have not worked with further training after it is trained for some sort of data. And I think after training, if you add more data and start to retrain it again, I think it starts to take more time compared to when you train all of the data set together. So I have really no experience, but this is something that I think would happen.
Okay, but you would not start training the model from scratch, but you would just make a little adjustment to weights, to the already pre-trained weights.
I know, but it depends on the optimization algorithm for training process. And I'm not at the moment, I have not tried that. So I cannot comment on that, but it can be a good idea.
Right, thank you.
You're welcome.
Who was first? Eugene, please.
So just a bit controversial. So you take your past results, you train the model, and then you use that to put your initial conditions, and that accelerates them. Have you tried, just as a control, just choose from among old cases the one that's closest to your new case and initialize with that? So let's say you've run 100 cases, you run number 101, and you have one or two parameters. You can search parameter space in your database, old cases, and just use that as initialization. I think you'll find your efficiency, and then you can do what he said by just constantly choosing the latest. Your acceleration is quite remarkable in that context as well. So my challenge to you would be is to compare the efficiency you gain from all the complexity of machine learning compared to just choosing the best initial state from among the cases you ran already. Understand what I'm saying?
Yeah. So we don't know really so the question is, if we don't use machine learning model, we just we use the prior solution and choose one of the most closest to the current problem that we want to solve. So there must be some algorithm to search that automatically, which one is the most close to the, and we cannot make sure because sometimes a small change in the geometry can make a huge difference. So It can be an option, but machine learning automate that for us. So it learned from all of them. For example, we want to solve 1,000 problem, and we want to automate that. So what is the algorithm to find out which is the most close to the current problem that we want to solve at the moment? So there must be some algorithm to find that.
So that's you just make the vector representation, you take the vector magnitude difference and you choose the one with the smallest difference. But just order the database to the vector size.
I never tried that, so maybe.
I think it'd be interesting because machine learning is very interesting, but sometimes.
Yeah, sometimes we can have better options. Yeah, of course.
I think there might be a difference in dimensionality. So if you have just one parameter that you're varying versus if you have like 10%, 20%, then at some point machine learning, might give you a better explanation of that estimate.
It will give you better, but the question is in terms of efficiency.
Yeah.
If it's advantageous to go through all that hassle.
I would have to try it.
Yeah, something that we can try.
More questions?
Yeah, okay. Yeah, I have a small follow-up to this, and it's connected to like separating spatial complexity of your problem from parametric complexity, and then maybe, yeah, did you think about like decomposing your input data, since you are interested only in like prediction initializer? Did you think about decomposing your initial data or input data through like COD or something like that? So it will take away your spatial complexity, so the problem size will not be problem anymore, and you will have the like parametric complexity or temporal complexity or something like that on the other side, and you might be able to use your neural network to estimate these coefficients, so only parametric complexity. So the question is basically, did you think about it, or do you plan to work on this area? Because it can significantly reduce your dimension of input-output problem dimension.
Yeah. So as far as I understand, I think you are suggesting to change the input to some simpler one to find the relation easier.
The output, exactly.
Yeah, output. Yeah, output.
Interested in I don't know, displacement probably.
Yeah, displacement.
So, and the displacement field could be decomposed using the proportional decomposition into some spatial modes and parameter-dependent coefficients. And if you have a mesh, if you have 500 solutions on a mesh with 10,000 cells, then the dimension of the spatial mode will be 10,000, but you will have only 500 coefficients to say. So this can reduce the problem.
Yeah, that can be an option, and I think a good suggestion, because the output here, if you increase the cells, as you said, number of cells, the output, for example, for 1 million cell is 1 million output. So if you can find a function to approximate this solution or POD or some other function and try to search for those functions rather than searching for displacement. Yeah, that's correct. And we can work on inputs and outputs. Also inputs. I use cell coordinates and you have 1 million inputs. So actually I haven't, my work, the focus on my work wasn't on the optimization of the architecture of the network, but on the idea of ML initializer. But of course, if you work on the inputs and outputs, that you can get a better, maybe less training time and better results. Yeah. Thank you.
All right, further questions? Then, okay, there are no online questions, I think. So then let's thank Emad again.
Thank you.
All right. The second speaker of today's session is Josh Williams, and he's going to talk about neurostochastic differential equations.
Thank you. Yeah, thanks for the introduction. So the main focus of my PhD is kind of on improving the predictive quality of modeling for drug deposition in patients' airways. So in our case, we have this patient CT scan, then we model the inhalation of air and then also aerosol drug particles if the patient has asthma, for example. And then, so specifically what I'm going to speak about today is the influence of turbulence in this case, and then how it influences the particle dispersion, and then with the kind of end goal of improving predictions of deposition. So for our case, because we have complex geometry like you can see here, and then also a high Reynolds number flow, then we can't really fully resolve the turbulence. So we need to filter out and model the smaller scales like you can see here. So within each cell, we have kind of fluctuations that are unresolved. And if the particles have really low inertia, like aerosols, then they're heavily influenced by these fluctuations. So one way that we can model this is using stochastic differential equations. So if anyone has heard of Brownian motion before, it's essentially this. So we treat it with the evolution of some variables. So in this basic example, x is the sum of a drift term, which is deterministic, plus some random diffusion term, beta, b, multiplied by a stochastic Wiener process, which is just a random number sampled from a Gaussian distribution with zero mean and variance dt. And so in this little 1D example, we can see the influence of each term, where on the left we have a zero drift with a non-zero diffusion, and then this kind of creates a spreading of the particles about zero mean. And then on the right, we have a non-zero drift, but a smaller diffusion, and then this creates kind of a smaller variance. So it's similar to uncertainty or Gaussian process, if anyone knows that. And then also now the particles have a general trajectory. It's not just centered on zero. But the existing models for turbulent dispersion have some issues that we found. For example, they don't have correct scaling of the particle velocity in decaying isotropic turbulence. It's kind of a fundamental condition for a physically consistent model. So we wanted to try using a data-driven model to improve this. So if we perform a highly resolved simulation like DNS, and then we can filter it and learn kind of the mapping between the two states. So in this study, we aim to train a data-driven model for turbulent dispersion on particles. So in this case, we use neural networks to learn the unknown terms, drift and diffusion, in our SDE. So we call this a neural SDE. And then we wanted to assess the performance in a homogeneous isotopic turbulence. So a little overview of the modeling framework. We have the filtered Navier-Stokes equations with one-way coupling because the flow is quite dilute. And then we have point particles moving throughout the domain, like you can see here in the bottom right. And so this is essentially just a large eddy simulation where we have the fluid is governed by the mass conservation, which is just the divergence of the filtered velocity field, UF tilde. And then we have the conservation equation with time derivative convective term balanced by the pressure gradient plus the divergence of the resolved viscous stresses minus the subgrid stresses. And so the subgrid stresses are unknown. We need to account for these. And so we just use an eddy viscosity model for this, where the subgrid stresses are based on the subgrid kinetic energy and the subgrid viscosity multiplied by the strain rate. And then for this, we can use any model like dynamics, Magarinsky, or in this case, we use the whale model by Nakud. Then for the particle phase, we have Newton's equations of motion, where we just account for drag on the particles. So the evolution of particle velocity is based on the relative velocity between the particles, UP, and then this variable US, which is the fluid velocity seen by a particle. And yeah, generally, if what we do for US is it's just the fluid velocity in the cell interpolated to the particle position. However, if we have some unresolved fluctuations within the cell, we need to account for these, so we have an additional transport equation. And so this is where our Langevin model from the start comes into play, where we have the evolution of US is based on the drift term, which is this parameter G, multiplied by the difference between US and UF. So when the flow is laminar, this term dominates. And then we have the diffusion term, again, multiplied by the random vector. And so the NN superscript notation shows that we approximate these terms with neural networks, where the inputs are just based on the subgrid length scale and the filter width, and these are normalized, shown by the star notation. And then because it's isotropic case, these are just scalar values, and we multiply them by the identity tensor. And yeah, it's important to note that the inverse of G is essentially the time scale of the the stochastic model. And then this is kind of in competition with the particle timescale. So if the particle timescale is much larger, then the particles will have high inertia and aren't really influenced by the fluid fluctuations. And then, yeah, this is the model inputs, how we get them. So timescale is just k over epsilon divided by the Kolmogorov timescale. And then the filter width is just divided by the Kolmogorov length scale. And so for our simulation, we have decaying homogeneous isotropic turbulence at Reynolds number 9, 33, and 100, a little box in the way. But yeah, then we run kind of DNS simulations at 256 cells in each direction. And then to generate the filter data for training and testing, then we apply a top hat filter convolution at varying filter width. So here you can see the DNS velocity field and then the coarsest filter width. And obviously it appears much smoother and the peaks are much less velocity. So this will influence the particle velocity and clustering, this kind of phenomena. Then for the neural network, we have a feed-forward neural network with only 2 hidden layers and 120 neurons per layer. So it doesn't actually take much data and kind of computation to train it. Then we have, to generate training data, we have the simulation timeline where simulation starts at T0, runs all the way up to Tn. We save the DNS training data every 20 time steps because obviously it's a really big mesh, can create a lot of storage. So then if we have various cases, you can get into the terabytes. And then we essentially learn by incrementing the velocity from T0 to T1 and then comparing the velocity at T1 with the DNS data. And then we do this for kind of every interval. And then, yeah, the loss function is a little bit more complex because it's a stochastic problem. So there's several more terms. I can go into that later if anyone wants to discuss it. But yeah, essentially we just minimize the difference between the neural network and the data. Then, yeah, for the OpenFOAM implementation, we filtered the fluid velocity field using this library coursing foam, which is on, all this is on GitHub. Then we extract, well, yeah, we extract the subgrid kinetic energy and dissipation rate using like some additional add-ons to this. Then we created a new dispersion model class, which extracts the model parameters from the neural network. So we have our neural network trained in Python. Then we need a kind of interface between C++ and Python. And so this uses this Keras C++ library. And then we integrate the SDE in time following this numerical scheme. And then, yeah, we make some small modifications to the solver, like one-way coupling, and then we solve for the fluid before the particles. And then, yes, so first of all, we perform a priori analysis. So this is literally just integrating. Each marker is where the particles have been integrated one step. And so we do this for varying filter width using all the snapshots from the simulations. This is showing the decay of turbulent kinetic energy with time for the DNS, which is a red line. And so we can see that by a lot of the kinetic energy is lost in the filtering process, which is the green dots, especially on the larger filter width. But the neural network kind of recovers the correct turbulent kinetic energy and essentially is mesh independent. Then, yes, we take this same kind of setup and then we perform a posteriori analysis. So fancy word for running OpenFOAM simulation at the same Reynolds number. And then, yeah, again, we can see that our implementation is pretty much spot on, a little bit of an underestimation, but yeah, we can see some improvement with the neural network. Then again, a posteriori analysis, but now adding inertia to the particles. This will vary the trajectories and then also the kind of fluid properties sampled by the particle. So we have Stokes number 0.1, 1.1, and 5, which is kind of low inertia, moderate inertia, and high inertia. Then, yeah, in all three cases, we can see significant underprediction in the kinetic energy from the LES alone. Then when we add the neural network, we get great agreement with the DNS data. And then, so as an additional metric, we can quantify the particle concentration. That's kind of the main property that we're interested in, actually. So this is essentially how clustered the particles are or how uniformly dispersed they are. So here to quantify this, we use the number density function, essentially just calculate the number of particles per cell, and then plot the probability density of this. So if the number of particles per cell is 1, it means that the particles are uniformly dispersed in all the cells. So we can see that the neural network and the DNS agrees very well with the mean and the variance of the PDF. However, the LES with no model has much larger variance, which shows when we look at the visualization here, there's areas of no particles and then these kind of dense clusters, which aren't apparent in the DNS and the LES with the neural network. So this is kind of artificial clustering, which has also been confirmed in the literature. And then we can see that we get, again, for Stokes number 1.1 and 5, excellent agreement with the DNS data. And then to test on a kind of unseen case, we performed Taylor-Green vortex flow compared to simulation data in the literature, where our mesh is 4 times coarser. And then we have Stokes number 1 and 5. So if anyone doesn't know what Taylor-Green vortex flow is, it's essentially a visualization on how the flow field evolves. So we get these kind of box-like flow structures, and then the low inertia particles will become trapped and circulate in these. High inertia particles will pass through and are essentially not disturbed by the flow. So this time we quantified concentration using the Voronoi volume distribution. So it's a little bit different, but just to stay consistent with the DNS data. So in this case, if the Voronoi volume goes towards 0, then this means that the particles are all right next to each other. And then we can compare this with the Poisson distribution, which is essentially just random uniform dispersion. And then, yeah, for both LES data sets, we can see at the start of the simulation, they agree quite well with the DNS. However, as the simulation progresses, we get good agreement with the neural network and the DNS, but again, we see some kind of artificial clustering from the LES. And we think maybe this is due to some numerical issues like interpolation, but this is kind of really recent preliminary results. And then, yeah, for Stokes number 5, again, at the start, we see really good agreement in all 3 cases. Then as the simulation progresses, the DNS and the neural network tends towards the Poisson distribution, so they're kind of uniform dispersion. And again, we see a little bit of clustering for the LES with no dispersion model. So to summarize what we've done, we developed an approach for data-driven modeling based on particle-laden DNS with one-way coupling, and it gives improved predictions of particle statistics like kinetic energy decay and preferential concentration. And then we can see that the results in isotropic turbulence generalized to Taylor-Green flow. And then so we want to follow this up with a future study on turbulent channel flow, where we may need to add some additional terms to account for the anisotropy, velocity gradients, etc. And then eventually progress to actual application of drug deposition in lung airways. And then, yeah, the code will be available on GitHub after I publish the preprint. But the main message is that LES should be complemented with some dispersion model and simulations of particle dispersion. So, yeah, otherwise you get really mesh-dependent results like kinetic energy. And we feel that the neural SDE is a really good approach for this, as it's been quite well validated here. And yeah, I'd just like to thank my funders, the Carnegie Trust, and then also advertise I'm open to job opportunities. And that's me.
Thanks a lot. Another really clear presentation. Are there any questions? Yes, please.
Thank you for a very nice talk.
Thanks.
I was wondering, what adaptation do you have to make if you consider particle collisions?
Collisions. Ooh, so well. So I need to repeat the question, right?
Yeah.
Okay. Yeah, the question is what adaptation for particle collisions? Well, so first of all, if the particles are colliding, this is 4-way coupling, right? But then first of all, there needs to be an adaptation for 2-way coupling. So you need to include the solid volume fraction, for example, maybe relative distance between particles. There's some kind of physics-based models for 4-way coupled dispersion in RANS. yeah, if you like, I could send you the paper after. But yeah, so then they just have two-way coupling plus an additional transport equation for the kind of collision frequency. It's called, I can't remember what the property is called, but it escapes me. Yeah.
One, if you try, the first is that if you try to compare this new approach with the traditional Langervan equation, and the second one is if you tried to the limit for the Stoch number that goes to 0, because in that case the dispersion, the dispersion is
Yeah.
essential.
So yeah, the question is, have I tried against the traditional kind of physics-based model and then in the Stokes number 0 limit? Yeah, so for the Stokes number 0, yeah, we quantify the kinetic energy decay here. So yeah, we don't have the results for the concentration, but it should be kind of uniform dispersed as well. And then for the physics-based model, yeah, I'm glad you asked that. I have some backup slides. So first of all, yes, so for the physics-based model, this is the closures. This B term on the top is for high inertia particles, so we can just forget about that for a minute. Essentially, G is epsilon over K. Then we have a nice little proof here, where, yeah, so if G, the time scale is 1 over G, then in the case, yeah, if we kind of give this relationship, it's delta over square root K. If the flow becomes laminar, the time scale should go to 0. But then obviously also the kinetic energy is going to 0. Therefore, we get this kind of, the time scale actually goes to infinity for large eddy simulation. And so a lot of the studies, it's kind of fully developed turbulence. Whereas, yeah, if we have turbulent or decaying homogeneous isotopic turbulence, what you see here is because the time scale goes to infinity, the fluid velocity can't adapt. So it has a history, essentially. And then, yeah, if we have a channel flow, the distribution of tracer particles should be uniform, because, yeah, the density distribution of the fluid is uniform. It's incompressible flow. Then what happens is the particles here, they move towards the wall, but then they still maintain their velocity as when they were kind of in the mean flow. So then they all cluster at the wall, and it violates the laws of physics.
More questions? I would have actually one question. So did you apply some kind of normalization to your features and labels? And for the Taylor-Green Waters case, did you somehow check that if you are like extrapolating over feature space?
That's a really good question. Oh yes, so the question is, did I normalize the features and labels, and did I check if I was extrapolating in the feature space? So yeah, for the features, yeah, we just applied a minimum maximum normalization. So yeah, the maximum value of all these in the training data is 1. For the labels, yeah, I think I normalized it by the maximum velocity per case. So obviously we have 3 different Reynolds numbers. Then I have the maximum one for each case. And for the Taylor-Green flow, no, actually, I didn't check that. That was a good idea. I will.
Right, let me quickly check if there are some questions from the online participants. Doesn't seem the case. All right, then let's thank Josh again.
Thanks.
All right, the last speaker in this session is Lorenzo from Chaos, and he's going to tell us what he can do with machine learning to enhance Flamelet modeling.
Thanks for the presentation. So today I will present this work which combines the neural network with the Flamelet-Progress variable model to close the turbulent combustion in the OpenFOAM framework. And this work has been done in collaboration with Chaos and Sapienza, where I'm doing the joint doctorate. How can I? Okay. So first of all, I've introduced the physical to the physical problem. After that, the neural network contribution. I will describe the different test case with which we did all the validation steps. Doesn't go. Okay, so in order to simulate combustion, we need the normal continuity equation is not enough because we need to introduce all the effect of the different species. So we need to introduce a number of equations to transport the mass species, the species mass fraction. That are dependent on the number of the species that are in our chemical kinetic mechanism. So for this reason, the system becomes very huge because if you think to methane, which was mechanism has 53 species, so it means that we have to solve 58 equations. And if the mesh is very large, it means that the system becomes extremely computationally expensive. So for this reason, tabulated chemistry and all the related reduced order models are computationally attractive because they allow us to reduce considerably all the computational cost by pre-tabulating all the thermochemical properties. So in this case, for example, with the Flamelet-Progress variable approach, we reduce from the 53 species of methane plus the temperature, we reduce to only two variables, the mixture fraction and the progress variable. So it's particularly convenient. But of course, we lose something in terms of accuracy because, for example, the Flamelet-Progress variable model is particularly adapted for a non-premixed flame. But if we move toward the premixed limit, we need another kind of model. So for this reason, some newer models have been developed in the Flamelet-Progress variable framework that are able to take into account of all the different regimes. But of course, you increase the computational cost, so you are coming back. So for the goal of this work is to try to make these more complex but accurate models feasible for a Flamelet-Progress variable simulation in OpenFOAM. Where should I be? Okay, so the reacting transport equations, if we use the Flamelet-Progress variable approach, reduce to the continuity equation, momentum equation for the fluid part, and the chemistry is solved with the transport equations of the progress variable and mixture fraction. And since we need to close the turbulence for the combustion side, we need to transport also the variance of the mixture fraction. I didn't understand what is the... Okay. No. Perfect. So from the tabulation side, what we are going to solve are the steady Flamelet equation that basically employ the mixture fraction Z, which is a variable, and the scalar distribution rate of the mixture fraction, which indicates the degree of diffusion of our flamelets, and it is a parameter. And it basically indicates the derivative of the a way to describe the gradient of the mixture fraction. So we can solve this system for different chi, and we will obtain different tables. After that, we apply a sort of table inversion. We compute the progress variable, which is only a sum of the most important species, the species mass fraction, and we do this table inversion for which we obtain this kind of tabulation. Why this is convenient? Because if we describe the flame through the mixture fraction and progress variable, some characteristics of the reaction zone are better captured. So this is a better approach. And then, if you want to include the effect of the turbulence in the table, what we do, we assume a beta PDF for the mixing, and we apply the convolution with the beta PDF. So basically, we introduce the third variable, which is the variance of the mixture fraction, and we can build these lookup tables where we are going to read all the species mass fraction and the temperature, which are only observables of our simulation, meaning that they are not necessary for the computation of the for the resolution of the simulation itself, and the density, the density, viscosity, and progress variable source term, which are necessary to resolve the system. So the solution algorithm, basically, as I mentioned, we pre-compute all the tables, for example, with Playmaster, and we apply the convolution. Now, the traditional approach basically reads directly this table and interpolate the results according to the values that we have in the field. And for example, we developed this solver with OpenFOAM that we named FPV-FOAM. Or this new approach is the one of using build a neural network. In this case, this will allow us to interpolate all the tables for all the different parameters, and we can build this table with PyTorch and couple OpenFOAM with libtorch, which is the API for libtorch, in case we want to use a C++ code, and in this case read on the fly all the neural network. So our neural network, basically, we generated the tables with Playmaster. We used the 80% for training, 10% for validation, and 10% for the test. We performed a Bayesian optimization in order to retrieve all the best hyperparameters to describe the manifold. We performed the training with the GPU cluster that we have in-house, and we use a selection matrix to determine which is the best neural network. The minimum between the error, the minimum of the sum between the error and the variance of the mean square error of the progress variable source term. Why? Because we want that we want that this variable doesn't fluctuate a lot during our prediction, and this variable is also this parameter is also the most important because since it is a source term, is particularly important during the evolution of the source during the evolution of the progress variable, and can make all the code blow up in case it is badly predicted. So with an a priori, if we want to, after performing the training and select the best network, what we observe is that the temperature, density, and viscosity, the error is less than 3%. So basically are well predicted. And the source term, the maximum prediction, the maximum error that we can observe during the prediction is about the 50%, which seems quite a lot. But since the scaling of the neural network for this variable is performed based on the magnitude of the source term, and our simulation is and the progress variable is sensitive only to the magnitude of the source term. At the end, we will see in the future in the next slides that this will not really affect the quality of the solution. So we perform a preliminary test case with two meshes, one with 34,000 cells and one with 250,000 cells, and we used basically the same initialization of the SanDIA-D, which is a canonical flame. So we have a large data set, a large experimental data set that we can use for validation. In this case, this is not at all a SanDIA-D flame, but what we wanted to do is to try simply the code with the table and the code with the neural network to try to see if the prediction of the observables is the same. So we use this setup, and what we observed is that for both the meshes, for both the NN and the direct table reading, we have basically the same results. So basically it means that the prediction of the source term, which was the critical value before, does not really affect the solution. Why? Because as I mentioned before, it is really sensitive only on the magnitude and not on the exact value. And then if the magnitude is properly predicted, the deviation from the original result is really small. So for now, in this case, we can say that except for the temperature on the peak value, that we have this over prediction in the reaction layer, we can say that okay, this is due to by the fact that the progress variable source term is not very well predicted. But at the end, in terms of the general solution, we can say that it's fine. And basically, we have the same, we can arrive to the same conclusion also for the progress variable source for source term. So now, if we want to move forward, we can see how it scales. So if we increase, we can try two models that basically have 3 layers and 100 neurons and 8 layers and 100 neurons. And what we observe, as expected, is that the larger architecture of the network, of course, is slower because it has to do more computation. So what we want to do is to find the best network, but that is also small. And what we observed here is that if we increase the size of the mesh, the network performs better than the table reading. Why? Because this is in the scaling procedure of the network. Because when in OpenFOAM, basically we are going to create the input tensor for the network, one input tensor per each thread that we are going to use. So potentially the scaling goes to the limit of 1 cell, because if we use the same number of threads as the same number of cells, basically, of course, the prediction will be the fastest. Of course, we will have the problem for the communication in the fluid dynamics. But basically, with this, we completely eliminate the problem of the scaling for the chemical part, and also the problem of the shared objects if you want to use the table, because of course the neural network is very small in terms of memory occupation than a table of 1 gigabyte. The network weight only 10 mega, 20 mega according to the architecture. So now we want to go toward a real SANDI-AD. So we increase drastically the number of cells. We go to 40.6 millions, and we perform the simulation with the traditional table reading, and we use this quasi-steady state simulation with the ANN model to check how it goes. So basically, the first thing that we observe is that if we use the FPV table, it takes around 2,000 seconds. If we use the ANN, it takes 1,500 with using 40 threads and for 100 time steps. So we can observe immediately 30% of reduction on time. And the 20, yes. So, and the other thing is an optimal qualitative agreement. Now, if we check 2 different slices at 2 different stages from the nozzle, far from the nozzle exit, what we observe is that the prediction is basically the same. So in a highly turbulent case where we have all the diffusion, the turbulent diffusion that increase the mixing, basically the effects that we observed before in a quasi-laminar case are completely tends to disappear, and this actually helps us for the progress variable source term, because basically the effect of the mixing reduce the impact on the accuracy of this sensitive term. Now, so we always did comparison between 2 different models, but not with the real results. So what we want to do now is to do a complete real validation of our model. So we increase again the mesh with 8 million cells. We add a fully turbulent pipe coupled with the simulation to reproduce the exact turbulence at the inlet, and we test 3 different networks, and we also check the species that I've never mentioned before. So in this case, we compare the networks again against the experimental results, and what we observe is that they have a general qualitative agreement. The velocity is decently reproduced. The mixture fraction is actually a bit translated in the downstream. So basically, it means since the velocity is reconstructed and the mixture fraction is only advected, it means that we have a problem in terms of diffusion. So we have to be careful. But this is a general problem of the Flamelet-Progress variable model when we define the diffusion of the mixture fraction and the progress variable. The another conclusion that we can say that the neural network doesn't different, even if they have different architecture, one is larger, one is smaller, and so we expect a different degree of accuracy, the prediction is more or less the same for all of those. The other particular thing is that the peak value, where all the reactions are happening for the species mass fraction. Why we can observe this difference? Because since the neural network is large, we are going to predict 20 variables. We can expect that if the variable, like the species mass fraction, is highly nonlinear, the prediction might be different. So we have to be careful in this case. But since the code is really flexible, we can say, okay, if you want to predict this species, since are only a post-processing, we can develop an ad hoc network only for the species that we are interested. So in that case, we don't really care about the species. If we need it, we can develop this network and increase the accuracy of the prediction. So why we are doing this? Because this model, as we said, the advantage of using this model is only a little speed up. So we want to increase the accuracy of the Flamelet model. So for example, this newer model that we choose as a target, basically what it does is solving the Flamelet equation in the mixture fraction and progress variable space. So we don't perform the inversion of the table, and this will actually cover the entire span of the combustion regimes, which is our target, because in this way we can capture the exact combustion regime in each point of our field. So, but what is the price that we have to pay to use this model is the increase of the dimensionality of the manifold, because we have to include progress variable mixture fraction and all the scalar dissipation rates of the progress variable and mixture fraction and the cross correlation. This basically will increase the accuracy at the second order, because we include the effect of the derivatives of the progress variable and mixture fraction in the model itself. And when we have to include also the effect of the turbulent closure, we need to include the variance of the mixture fraction, the variance of the progress variable, and the covariance. So our manifold should become 8-dimensional, which is quite large for performing a traditional interpolation, and the neural network or another way of interpolating the data becomes mandatory. So what we try to do is to use, first of all, the 5-dimensional manifold. So we eliminate the turbulent closure and we try to perform a laminar flame computation. Basically, we obtain, with the first thing that we observed is that to obtain robustness and accuracy of the neural network prediction, we cannot use a single neural network for all the variables. What we need to train 5 different networks, because otherwise the accuracy of all the source, especially for the source term, will be completely gone, and we will be useless. Then we compared these laminar flames against the finite rate method, which should be the most accurate in OpenFOAM, and what we observe is that the flame is there. I mean, we could develop a flame that is quite similar to the experimental results. The main difference is observed in terms of width of the flame and length, but this difference for laminar flame for the laminar flames becomes crucial, the effect of the diffusion. And as I mentioned before, the diffusion is a critical point of the Flamelet-Progress variable model. If we go toward the turbulent case, we don't really worry about it because basically the turbulent diffusion will hit completely the effect of the laminar diffusion coefficients in all the other effects. But in the laminar case, when we are in the multidiffusive, and we should include all this effect, it is expected that between a Flamelet-based model and the finite rate, we can have this kind of differences, because the flame tend to scale with the viscosity and the diffusion. So for this reason, for now, the results are satisfying. What we want to do next is to include the effect of the variances in the training, and so have an 8-dimensional manifold and try to perform a complete SAN-D with this manifold, and try to attempt to simulate more complex burners that involves all the regimes, for example, like the Darmstadt burner that I showed at the beginning. Thanks for your attention.
So generally for FPV tables, the sourcing progress variable sourcing is very sensitive, but you show that it's actually not that sensitive, because even if your prediction has 40% error, the result is still quite the same. So I'm wondering what is the main reason of that, and also what is the cause of that 40% error?
Because they are like, okay, the question is basically generally it was observed that for the FPV, the source term is sensitive to the progress variable and vice versa, and which is the source of the 40%, 50% error. So basically the 50% error is the comparison between the predicted values and the ground truth, basically the real table. And why it's not sensitive? Because we found that the source term is sensitive to the magnitude. So basically the 50% error, basically if we have the source term that is 100 and we use 150, it's fine. I mean, what we found is that the prediction changes a bit.
Have you seen in your simulation whether you actually cross those points?
Yeah, because basically the higher points, the higher error is when the source term is really you can have 2 points where you have large error, or when the source term is close to 0. So basically you have the 50% of error, but basically can mean that you have the source term of 1 to the power minus 8 and 2 to the power minus 8. In that case, it's close to 0, so it doesn't really affect the solution. Or in the reaction zone. In the reaction zone, you have that, for example, can be 120 or 180. But in that case, you observe the difference in the average values. But the difference is really small compared to the difference in terms of the source term. Why? Because we found that if we change a bit the magnitude of the source term, for example, if we perform a simulation with the double of the source term, directly we force the source term to be the double in the traditional FPV table, we found that the solution varies just a bit if we don't change the order of magnitude. Of course, if we move from 800 to 1600, you find a real you find a larger change, a larger deviation. But if you go from 100 to 150, at the end is reasonable. You're welcome.
More questions? So I would have one question. So in the Bayesian optimization loop, how many networks do you actually train?
A lot.
Because I saw numbers like 2,000, 3,000.
No, yeah, because we have the iterative thing that goes further. So yes, since fortunately in Kausta we don't have problem of resources, and to train a neural network takes around 1 hour. We can use 40 GPU at time, so I gave batch till 2,000 networks per time and see what is the best.
And you also had on your slide MSE and also Ruberos.
Yeah.
So this was like one.
Yeah, one tuning parameter in the generation of the network.
Right. And okay. And how did you end up with this particular network? So did you because I would have expected that maybe increase the size by a lot, that maybe you get a better accuracy or you can drive the error.
Yeah, but there is a certain threshold. I mean, it's really dependent on the learning on the hyperparameters. So basically, sometimes we found that we performed the optimization and we found that a really huge neural network that performs basically exactly the same way rather than a very small one with a variation of the 0.1%. So, okay, this is really needed. Maybe in the source term, yes, but for the other variables, if the density is 0.01% better of the other, it doesn't change really a lot in terms of the simulation.
Yeah, can I just ask a technical question? What activation function did you use on your different layers?
ReLU.
Okay, on the output layer as well?
Yes.
And then do you know what you initialized the weights as?
No, I don't. Oh my God, I don't remember. Because I think that I was 0. Yes. Yeah. Because I don't think that we operate in that direction.
I found sometimes like it can kind of help if you, especially when you're changing the layers, the number of neurons, for example. Yeah, because you get your output will change based on the number of neurons. If you just have random uniform distribution, and obviously if you add more neurons, it sums up to a higher value. Then you get some certain initializations at scale based on the size of the network and to help.
Okay, good to know. Thanks.
PyTorch default initialization takes all of this into account.
Okay.
So I don't have the author in mind right now, but it's something based on the number of neurons in the previous layer.
The Zapier.
Sorry?
There's Zapier initialization.
Yes, yes,
Yeah.
yes. Right, further questions from the audience here. Otherwise, I will quickly check if there are some questions from the online audience. Okay. That doesn't seem the case, then let's thank Lorenzo again.
All right, everybody, thanks for joining this session, and see you all probably for the Splash Talks.